kind of sort of the things that we want to talk about. So last time we talked about neural networks, and so we may come back to it later if we have time. But basically, the idea was that by composing linear functions interleaved with like element-wise nonlinearity, we can construct parametric families of nonlinear functions. Okay, and we saw, for example, that like you can combine. So this is how usually you like represent these. You have like the input, and then it goes through a linear map, and you have this hidden layer, and at this hidden layer, so the elements are called like that. Sorry, the nodes are called neurons, basically. So implicit in those elements or in these nodes is the nonlinearity. So you apply basically a nonlinear operation to the linear map output, and so that gives you the hidden layer, and then you can like compose this with another linear map followed by elements like nonlinearity and so on, and so you get these more complex functions that are referred to as networks. So you can see like it has the shape of a network, things are connected to each other. And I think we discussed was this fully connected neural feed-forward neural network, sometimes referred to as multi-layer perceptrons. And someone asked me, like on a campus where someone asked, I've seen these, I was told, or like I was, I've seen that people reduce the number of nodes as you go along, and should we do that? So I don't have a general rule that you have to do it or you have to not do it. So these are neural networks. You can construct them. Some may be better than the others. Some way of combining things. The way that we constructed this, in our case, we had two inputs. So if you want to go like to smaller number of hidden units, it would be just one. So it wouldn't be that interesting. So we thought that if you like go like from 2 to like 10 and then back to 1, you could get interesting functions. You can also like do 2 to 10 to like 20 to like, you can go crazy with whatever you want to do and then come back. Now there are different formats. So this format that I mentioned here, I think it's called the U structure or something like that. So you go from big to like, you know, this is an image, you go to something small. This part is usually called an encoder. And then from something small, you go to something usually of the same size. And the idea is that you want to reconstruct basically the original image. So this middle guy would be the representation or the encoding of it. So you assume that this image can be like reduced to some smaller dimensional object, and then that can be decoded back to, so encoded and then decoded back to the original image. So you go from, let's say 10 to 2 to 10, or like 100 to like 8 to 100. And then the loss is basically trying to measure how close the output is to the input. And then you train the network using that loss. So this goes back to the idea of dimensional reduction. It would be like a nonlinear version of PCA, principal component analysis, which unfortunately probably won't have time to talk about. But hopefully you can follow the main idea that I wanted to convey is like the building blocks of neural networks are simple. And the main idea is that these would give you nonlinear functions that are parameterized by a bunch of parameters, and then you can fit those nonlinear models by gradient descent on a loss function. Okay, so all the machinery that we talked about, gradient descent or gradient descent of momentum, or other fancier first order moments, methods like this Adam optimizer that's in PyTorch, you can apply, and there's really not much in terms of let's say coding that you need to change, although like there's a lot to understand. So there's different issues that arise when you try to combine these. But for now, I'm going to leave this aside. So any questions about neural networks? there's one point about convolutional neural networks which I might come back to. Well, let's move on to some other method for now. I want to talk about the questions neural networks. Okay. Deep learning would be like do this many times. Like the depth of the network is how many times you compose. And you have to be like a little bit clever. But okay. There are a lot more to deep learning than just what I mentioned, but just the basic idea is that. And so there's another way of constructing nonlinear functions, and these are via feature maps or basis functions, and this leads to the idea of kernels. I just want to maybe briefly mention that. So suppose this is very different than neural networks. Another way of getting parametric models. Suppose I want to do like, yes, okay, feature maps, basis functions, etc. So that's the other topic. So anyone knows like what is the idea here? How can I like construct nonlinear? So let's say I have this idea that maybe my classification problem has this nonlinear boundary. So inside the circle is one class, outside is another class. So how do I go? So we have seen that logistic regression cannot sort of approximate something like that well. So like class, for example, 1, this is class 0. Is there like a simple modification that I might be able to? So maybe this is like really a circle. So let's say, for example, this is my optimal rule, the set that maps to class 0. Let's say it's like two-dimensional, and it's given by the circle, for example. So this is the situation. This cannot be achieved by so logistic regression and not have such optimal classes. Right, so for logistic regression, things would look like this. So the optimal rule would be x1, x2 such that like a, or let's say theta 0 plus theta 1 x1 plus theta 2 x2 is let's say bigger than or equal to 0 or less than or equal to 0, whatever you want to call it, doesn't matter. So it's like a linear or a fine function less than or equal to 0. It's like it's going to be like a hyperplane. It can't be like a circle. So is there a way that we can like modify? So like logistic regression. So like theta hat is that was sort of the ERM version. The loss was log loss here. So is there a way I can modify logistic regression, or like the model was something like this: y equal to 1 given x is equal to x, a sigma theta transpose x. So that's the logistic regression model. So is there a way I can achieve some sort of classification boundary like that? A simple modification that it can make. Yeah.
I'm not sure, but I think we have to modification on theta has xi and which x1 2 plus
x1 to the power 2. So where should, okay, so for example, I want, okay. Let's say start from this. I want my decision boundary to look like the sort of all X such that. So if I can get a model that has this property, the decision boundary looks like theta 0 plus theta 1 x1 plus theta 2 x2, let's say plus theta 3 x1 squared plus theta 4 x2 squared less than or equal to 0, then such family of parametric models would be able to achieve what I want, because there is a set of parameters, like I can say take theta naught to be -1, this to be 0, this to be 0, and these to be 1, and you can see that that would give me that circle that I want. Okay, so I just want a decision, like a model such that the decision sort of function when I evaluate for class 1 looks like this. That's a good sort of step. So now can we like modify, let's say, can I modify this logistic regression in a way that achieve that? Anyone? So how did we get that something like this holds? How do we get that for logistic regression? Let's say the this is the class associated, the zero class according to Bayes' rule. So how do we get that in logistic regression? Right.
The feature instead of x1, it's a x1 over 2.
Instead of x1, we can, yeah, we need to change the features. Just how do we get from this to that? If you remember. If I give you this probability model, what is the Bayes rule associated with this probability model? The optimal rule, let's say. Delta star x would be 0 if this probability is less than 1/2, right? Bigger, less than 1/2, right? That was the decision rule. The probability that, like the optimal rule, bigger than 1/2. And when I do this less than 1/2, bigger than 1/2, what do I get? So this is the function is this, goes from 0 to 1, right? Bigger than 1/2 is the argument. So this thing is going to be equivalent to so in logistic regression, delta star x would be 0 if theta x is negative, theta x is positive. Okay, because above 0 the sigmoid is bigger than 1/2, below it it's less than 1/2. Okay, so that's how I got. So this, if you look at this condition, this is exactly this condition, assuming that we have an intercept. Okay, so the structure of this leads to this decision sort of class or decision boundary, linear decision boundary. Now, how should I modify this to get something like that? We're close, but exactly what should I do? I'm going to help you. So modify to y equal 1, given that if x is equal to x is sigma of, I should put something here other than theta transpose x. So what that would be to give me this like class 0. I need something here such that when it is negative, if the argument is negative, then that would be like the class associated with class 0. So what should I plug in, which is then negative identities? Instead of all x1 and x2 such that that holds. Anyone tell me? I'm just going to copy paste it here. Is this going to work? If I define my model to be like this, would class 0 be what I want? The answer is yes, because the optimal rule says class 0 would be vertices less than 1/2. Vertices less than 1/2 is where the argument is less than 0. So that's exactly the condition I want. So if I modify the logistic regression to look like this, then this model can achieve classifications or boundaries like that. Right, you can see the model now has, instead of 3 parameters, now has 4 parameters, and we have sort of constructed these extra features out of our original features. So seeing polynomial regression, this is very much like polynomial regression, just the logistic version of it. So what happened is I had original features x1 and x2. I added a feature of 1 for intercept. That was the linear model. Now I'm adding like x1 squared and x2 squared. Okay. And I have 5 features. Now I can treat these as like new features. This could be like z1, this is z2. I constructed my new features. In these new features, the model is linear. Okay, so if I'll call this z1 and z2, you can see that this is still a logistic regression model, but with these fake or like extra features that we created out of our original feature. So assume that original features was like x1, x2, z1, z2. If it was like that, then if we did a linear logistic regression, it would be fine. So we sort of constructed more features out of our original features. In this new domain with these new features, we're still like linear. So we can see that this is sort of, if I call this phi of x to be like 1. So this is like the transpose of this. This is in R to the 5. My model is really like sigma theta transpose times phi of x. So this theta is like theta 0, theta 1, theta 2, theta 3, theta 4. And this phi of x maps R2 to R5. Okay, so something like this is called a feature map. So you map your features via map to some higher dimensional space. In that higher dimensional space, the decision boundary is actually linear. So the decision boundary in this like x1, x2 space looks like a circle, but if you map it to this higher dimensional space, five-dimensional space, there you can separate everything by hyperplane, because in these new features, if you like think of them as new features, you have like x1, x2, z1, z2, you might have to imagine, and then dimension 1. In this new feature, like when you map your points, each data points, when you observe them, you're going to map each of your training data to this new space. Then you plot them in this new space, they can be separated by a hyperplane. So logistic regression is really not that limited. Once you allow yourself to like engineer your features by mapping them to a higher dimensional space, then you get a lot more flexibility. Does that make sense? So this operation is like there's no learning going on here, so you can just map your data into this. So you just create new features or covariates. Well, if you've seen polynomial regression, that's exactly what you do. And in fact, it would have been better to add one more feature. So it would have been better to add one more. Anyone knows what would be the one that we have to, like, not have to add, but it would be good to include? One, x1, x2, x1 squared, x2 squared. There's one missing, which would have been nice to have. To be able to get any polynomial of degree at most 2. This is fine. This model sort of can model things like this, but slightly better would be to include one more term. Yes. Okay. Good. So the statistician would call it interactions. Mathematicians just say. So I'm going to add this in between. So now this is going to be in R3, R to the 6. And this is better because then any linear combination, so if you have a general linear combination of this would be a general polynomial of degree 2 in 2 variables. So you can model any polynomial, basically any decision boundary that can be described by polynomial of degree 2. Another way of saying that this is better is that these form a basis for, so a 1, x1, x2, x1, x2, x2 form a basis for the space of polynomials in degree of of degree 2, of the degree at most 2 in variables x1 and x2. So so if I call this psi 0, psi 1, psi 0 of x is 1, psi 1 of x is x1. So x here is x1, x2. Psi 2 of x is x2. Psi 3 of x is x1, x2, psi 4 is x2 squared. Sorry, it's x1 squared. This is going to be 1, 2, 3, 0, 1, 2, 3. X1, x2. Psi 5 would be x squared. So psi 1, psi 2 as functions up to psi, sorry, 0, 1, up to 5 form a basis for, let's say, polynomial of degree 2. Sometimes written like this. R x1, x2. I forgot whether you put 2 here or somewhere else. So this is the class of all things that can be written as basically summation x1i, x2, j alpha ij over I and j, such that I and j are at most 2. Okay. This is a general polynomial of degree at most 2 between 0 and. So this space is a nice space for many reasons, and that's the basis for it. You can see that basically a basis means I can write everything here as linear combination of these elements. And this is really true. So any polynomial degree at most 2 can be written as linear combination of these. That's basically how polynomials of degree 2 are defined. So if you remember what basis is, that's really a basis. Okay. Sounds good? Yeah.
How we can determine how many features we should consider. We can continue into the power 3, power 4.
Sure. Yes. Yes. That's a good question. So this is a good question because whenever you start with logistic regression, you often don't ask this question. So logistic regression already like staying like at this level, right? This is good. People like work with this and never like question why we should stop at 1. Maybe we should go to 2 or 3 or 4 or no degree 20 or something like that. But it's a good question. It's not an easy question to answer. Okay. The entire idea of trying to, so this is sometimes called model selection. So if you are restricting yourself to polynomials, so you can look at the class of polynomials of degree k versus k plus 1 versus k plus 2, and you can ask which one I should choose. These are going to be nested, so the one that's smaller is going to be contained in the bigger one. So you're not going to use flexibility if you go to the higher model, like the bigger model. Model here is the class of functions, but you would lose something. So what would you lose? Why we don't go to like polynomials degree like 100? What would be the problem there, generally speaking? So what do we want to balance, sort of? So, efficiency? Sorry? Efficiency? Efficiency in what sense? Like, yeah, so like computational efficiency, you can see that the number of like features grow. So polynomial degree 2 in 2 variables, we have like 6. If you do 3, it's going to be much more. So you have like x1 squared, but you have all these and then x1 to the third, x1 squared times x2, x1 times x2 squared, and then x2 to the third. So the number blows up. Okay, so you get more and more like very, like computational efficiency is 1, but that's not the only one. Do you wanna?
Oh, I was just gonna say, like, accuracy and precision with simplicity.
Simplicity is always sort of one consideration that you can have. Simplicity or interpretability. So if you can fit a linear model and it works well, it's much more interpretable than having these, although like this is like not that complicated as well. So in this case, for example, you just add 3 more possibilities. But beyond, so from a decision theoretic perspective, interpretability is not as important. So if you care about like the loss, precision, let's say, if you want, precision and recall are like related to the loss. So if you care about the accuracy, for example, you can really go with the accuracy. So you can try to do like an estimate of the risk, which you have to do by an independent sample, which is tests. Like you split into training and tests, you fit a polynomial degree 1, degree at most 1 degree, which is linear map. You get most 2, 3, 4, 5, 6, and 7, and then evaluate the test error. At some point, the test error is gonna flatten out and then start to go up. The reason being that you start to overfit. That's what hopefully I'm gonna like try to make a point about. So if you really have like data that are about a line, if you have a sample size n, right? And if you have two, like here we have like a single variable. I have a single variable. And this line is like theta 0 plus theta 1 x1. Let's say they're really generated from a univariate model. Sample size is n, let's say 20. When I try to do you can do this with the usual regression. So you can map the features to the polynomial basis, but like to a higher state by polynomial basis. What happens is what would happen? So let's say if I start increasing the basis at some point, I like for a certain degree of polynomials, in this case, because you have a single variable, the number of basis functions is clear. So how many basis functions we have for polynomials degree k in a single variable? For more than one variable, it's a little more tricky. But I have a single variable, polynomials of degree k in this variable. How many functions do I need to describe them? Like basis functions, like this monomials. Okay. So a tree would be like theta 0 plus theta 1 x1 plus theta 2 x2. That would be degree 2. If I want to go to degree 3, sorry, x1. Up to degree k, I would need almost k, well, like a k plus 1 parameters, which is like including the intercept. So if I fit a polynomial degree k, and it happens that this ends up being like equal to 20. So I'm going to go up and I hit the sample size. What happens is that now I have like 20 parameters and I'm fitting a model which has 20 parameters to 20 data points. So if you do, for example, least the squares, you'll see that you can perfectly like interpolate the data. So what you're going to end up doing is like interpolating exactly through all the data points. This is what they call overfitting. Because you expect probably like if this is generated from a noisy model that the variation across that line are not actually signal, they're noise. But you're treating them as signal and then you're fitting to those as well. And on your test data, this is going to produce a big error because on the test data, they're going to be like somewhere else. So when I draw, for example, another point with this x1, next time in the test, it might be here, not there. And the line would be much closer than this one. By chance, I could be closer. Maybe this next time will also be here, which would be okay. But on average, this line is going to be, so they're going to be closer to the line than to this guy, right? So on average, because this is like going away from the line, if the actual model is the line, on average, this is going to pay a bigger price eventually. And so if you plot the test error, you can see easily that this is going to have a bigger test error. If you don't have noise, the things are a little bit different. The trickiness about like interpolation. So this is an example where interpolation is not necessarily good. If you have noise, whether you interpolate or not, you have to worry about interpolation, because especially if noise is high, when you try to interpolate, you're interpolating noisy data. And that's not what you would think is optimal. So the simple answer is like, if you care about prediction, do a training test split and evaluate on the test. Okay, so at least that gives you a criteria for model selection, which is tailored to our prediction. And you'd see that you end up doing something like this, and then it starts to go up. It's like as the degree of polynomial increases. In this case, it would be like the minimum is really, this is 1. It would be like that, because the optimal is 1, but usually you have like a bit near the 2k, if for example you have polynomial degree 2. Sounds good? Yes.
Does overfitting tend to be a big problem in building neural networks, since the neural networks tend to have tons of parameters?
Yeah, that's the actually good question, and that's sort of what people debate a lot. The short answer is overfitting tends to be in general problematic if you have noise. But the answer in general is much more interesting. So the actual number of parameters might not be what determine the complexity of the function class. So here, the space of polynomials, as you increase the number of parameters, it really gets complicated, sort of proportional to the number of parameters. So the number of parameters really measures the complexity of the class. In a neural network, the number of parameters might not directly correlate with the complexity. So there are many variations of the parameter which might give you the same function. So in that case, it's not so obvious that necessarily if you increase the number of parameters, you would hurt the performance. So suppose you have like, I should like come up with an example. So suppose you have this like a sequence of functions. They're all like, you have like maybe 100 of them, but they're all polynomials of degree 2, right? If I form a linear combination of them, I still get a polynomial of degree 2, although I have like 100 features, right? Each one, for example, suppose I have like the simplest that I can explain is, yeah, suppose you have like sigma 0, which is like x1 squared plus, so let's say in the case of 2, minus x2, psi 2 of x is like x is x1, x2. Psi 1 is like x1 plus x2, psi 3 is x1 squared minus x1, x2 plus x2 squared. Psi 4 is x1 plus x2 minus 2, or like, okay, it's like 2x plus x1 squared, and so on. So you can construct many like degree 2 polynomials, maybe 100 of them. And then you say, oh, okay, so now I fit a model with this many bases. So like psi 200, this is like x1, 2x1, 2 minus 3x1, x2, for example. Then I would have like theta 0, theta 1, theta 2, up to theta 200. So this may be a 200 parameter model. But really, once you like form the linear combination, it's really like a polynomial degree 2. So a lot of those parameters cancel out basically. And you're not going to pay that price. So at least my opinion is that something like this is sort of going on in Southern Ride. So it might help you like optimize. So once you have many parameters, it's easier to find an optimum because there are many solutions that give you a good solution. Like there are many variations of parameters that give you like a 0, like close to 0, a small training error. So that's one idea, okay, that the number of parameters does not necessarily correlate with the function, but there are things there that are a little bit beyond what we're talking about. So still you can construct models whose training error is close to 0. So you would be close to interpolation. And they still have good generalization property. Or properties. And that's a little bit harder to explain, okay? One explanation is that there's little noise. So let's say in image classification or things like that, things are really not noisy. So the models that you're fitting, you're overfitting, but you're overfitting to the right sort of noiseless model. So it's sort of, so if you imagine that your data points are all in this line, if I interpolate, I have to like stay close to the line. So all the data points are there, so I'm not going to pay a big price, even if I overfit. Although if I do polynomials, they're going to go like this crazy. But there are certain versions. So let's say, for example, if I do, okay, so this is like answer one. So the question that you ask is not an easy question to answer. It's like a question which is like people debate nowadays. Okay, answer one, answer two. Not much noise. So answer one is that the number of parameters does not necessarily linearly correlate with complexity. Not much noise here. Like in the case where there's not much noise, like zero, so this noise is zero noise. If you have zero noise, say on a line, you have things like this. If you fit a polynomial degree 100, you're gonna have problems because you're gonna do like this. Still, like probably like even like you'd see like sometimes you go like crazy. Could be like that, but occasionally it would do good. Polynomial like interpolation might not be good. There's a whole like literature on polynomial interpolation. Polynomial. Runge's example, if I pronounce his name correctly, check out Runge's example. So you could have like an interpolation which perfectly interpolates, but the error gets very big outside the range. But there are certain interpolating solutions that work well here. So for example, one that works here in the noiseless case is like if I have linear interpolation. Linear interpolation means I just linearly connect the points. Okay, so if I do linear interpolation, in general, like say the pointer like that, I'm gonna do like linear interpolation means sometimes called broken line interpolation. So linear interpolation is doing something like that. Okay, so like if you have noise, it's problematic. But linear interpolation, although it's like a non-parametric model, if there's no noise, it's going to match exactly the true function. So although you're interpolating, you're overfitting in a sense, you're not going to pay a price. It's going to exactly match the linear one. So you can see things are not as obvious. If you have no noise and you have a good way of interpolating, you might still recover the actual function, although you're sort of overfitting in a sense. This procedure that I described, like just linearly connect all your data points. Okay, it's not going to work that well when you have noise, but it's going to really work well if you have no noise and the things are actually linear. Okay. Answer 3 or so, you're gonna like maybe do research on it and then come up with your own answer. And there's something else that I want to talk about maybe later. We saw like a glimpse of it like in the last lecture. So there are many, so when you do these, there are many different sort of solutions. So it's not easy to, so when you do neural networks, the neural networks have, like give you like these non-convex problems, like optimization problems. And depending on how you optimize, you end up with different solutions. So that makes it more complicated to discuss what is exactly the nature of the solution. So you saw, I'm going to show you again, that the Adam optimizer produced a very different classifier than the one that we wrote our own like gradient descent. And I'm going to show you again. And there are some indicators. So it's still both work well for that breast cancer data. It turns out that both are like produce the same kind of test result, but it's harder to explain in that case what is exactly going on. So there is noise in that problem, And the model of a fit was big. So it's like 2 goes to 10 to 1. So you get 2 by 10, which is like, I think including intercept would be like 2 plus 1 times 10, which is 30 at 30 parameters. So it's a pretty big model, but it ended up fitting pretty well. So that is harder to explain. So noisy, and it's not gigantic, but you can also like, I can assign as a homework problem. You can just try to concatenate these things and still sort of works to some extent. Yes.
I have a question, this question.
Yeah.
So there is no any optimization method for determine the number of neuron in each layer in deep learning. We cannot optimize the number of neuron in each layer.
So
We can choose whatever we want.
that's sort of the thing. So it's sort of like a dark art, deep learning. So it's not a continuous optimization problem. So you can't optimize over the number of neurons. And if you have too many things to optimize, you're optimizing over many parameters. You want to optimize over the number of neurons. That would number of neurons is similar to the degree of polynomial. So you can try to do model selection, but it gives you a lot. So in deep learning, when you have like multiple layers, so you have many choices, how many in this layer, how many in the next layer, how many in the next layer. And then with convolutional neural networks, there's the window size or like the convolution filter. So how big that should be. And so if you imagine the number of combinations, it's a lot. So what they do, like what they call, like it's called hyperparameter tuning or like grid search, basically exactly what I described. So you choose it like a sequence of these values, and then you evaluate your test or validation and then pick them. And because the space is exponential, you have to like search over like the number of neurons in layer 1 and layer 2 and layer 3, and like the size of the convolutional filter. So it gets pretty big. But that's why you need big computers. Sounds good. Okay. What I want to do now is, any questions? What I would like to do is to tell you a little about regularization. And regularization is another way that you can, so instead of worrying about, so model selection by, let's say if I do polynomial logistic regression, I can choose like the degree by the procedure I mentioned, but grid search, or like what we call model selection, what they call grid search. K equal 1, K equal 2, K equal 3, K equal 4, each I can fit a logistic regression. And then I would pick the one and start doing it, and I plot the test error and it starts to go up. That's where I stop. The other approach is like pick a very large number and then use a regularization to restrict your decision. So that's the idea of regularization. So if you look at the, so that's what I want to do now. So like restrict complexity. So regularization as an alternative way to restrict the complexity. Or another way of like trading off bias versus variance. Okay, so that bias variance trade-off is sort of what is going on. So something like this, polynomial of high degree would have high variance, but potentially less bias. So if the actual function is really like polynomial degree 10, it is going to fit this better than a line. But a line has probably more bias for a more complicated function, but smaller variance. So it's a way of doing a trade-off. And this requires a little bit of math, which I'm going to do a little bit of it. And then the rest you're going to do in your homework problem, which I'm hopefully going to post soon. So the easiest thing to do is to consider linear regression. Okay, so we consider linear regression. linear regression. And so in particular, plus the L2 squared L2 penalty to penalty. So this is called ridge regression, which you have seen in your horror problems, ridge regression. So what it looks like is it's like I from 1 to n. Remember, there's a loss here. The general form is something like that. Ridge anything would be like this, plus lambda times theta squared. And then theta hat is argument theta in R. D, for regression, this is going to simplify to a quadratic loss, yi minus theta transpose xi squared. And so the problem is theta hat argument theta in RD 1 over n summation I from 1 to n yi minus theta transpose xi squared lambda. So this is the L2 norm. So this is just summation theta I squared I from 1 to d. Okay, so lambda is a regression parameter. And you can think of this as f theta of xi. So the function that you're estimating is this f theta. And once I figure it out, or once I estimate theta hat, I would have this prediction. So that would be my the prediction that I want to have. So roughly speaking, you can think of the actual model. So we're going to have like assume a generative model. So this is ridge regression. There's no assumption on the data distribution. At this point, you can do it always. But really, it's working. It's going to work if the actual model is linear in these covariates. So assume a generative model, like. So you're going to assume that expectation of y. Remember, this is this is really like theta star transpose x. Okay, so that was so we need to assume something about the joint distribution x and y, if you remember. And I'm going to assume that this is the case. Then I can write, for example, y as theta star transpose x plus the error, which is whatever is left, and call this epsilon. And then I'm going to assume that the variance of epsilon given x is for simplicity constant. Okay, so that would be my sort of model. So really, if you recall, this is the optimal rule under the quadratic loss. And so we're assuming that the optimal rule is actually linear in the covariates or the features that we have. And then I ask whether I can recover that or not. Really, once you, given what we understood, you can think of this as already mapped to a higher space. So this is like phi of xi. So in a polynomial, I picked a basis. I'm not showing that, but I'm picking a basis big enough such that my function is actually linear in that basis. Okay, so if you really want, you can think of this as these are really the feature, like mapped features. So this is phi of x after, but I'm not showing that for simplicity. So sufficiently like big feature space, it's good to assume that you're linear in that bigger space. Okay, so that's the setting. So we'd have a train. This is like at the population level, like a single generic sample. So we have the training data. Which is of the form, like from this model, which would be like yi theta star transpose xi plus epsilon ver like epsilon I ver variance of epsilon I given let's say xi, you write it like this, it's just going to be sigma squared. And then IID, so I from 1 to n, and then independent across I, so or IID across I. So independent samples, each one like yi is like this, plus some noise, which is like that. And at this point, I'm going to use some sort of like if you've seen like 100C, usually you work with the vector form. So x1 transpose here, up to xn transpose here, and I put theta star here. That's still like the same, so I can replace this basically with this is the same. Okay, this is the same as sometimes I write it as theta star xi is also the same as I can flip this the two sides. If xi transpose theta star, if you write it like that, you can see that this n by d matrix, this is d by 1. So this works out, and then I have epsilon 1 up to epsilon n. So this I call y, this I call x, this I call epsilon. And so I have my model is like y is equal to x theta star plus epsilon, which is your usual linear regression model. Okay, so that's the vector notation. So far, so good. Hopefully clear to people. And then I'm going to rewrite this. So let's take this, copy, rewrite the ridge regression estimate or estimator as so this is the one as follows. So this guy, I can write it as yi up to yn minus that x times theta. You can see this is similar, so I can just rearrange if you want. So xi transpose theta, you can see if I plug in theta here, it just gives me these. Let me do it like this. X1 transpose theta up to xn transpose theta is the difference of these two, so it's really y minus x theta. Okay, and this the entire thing is just this is this thing is really the norm of this L2 norm. Okay, so the L2 norm is I take y1 minus this squared plus y2 minus that squared. So you can see that that thing is really enormous squared. So this can be written as, I'm going to put a lambda as well, because it depends on lambda, argmin theta in RD 1 over n y vector minus x theta squared plus lambda theta squared. Okay, so that's the ridge regression estimator. Without the penalty, it's just the least squares estimate that you have seen in 100C. And if you're in this course, you can probably like solve this by, or you have done it already by gradient descent, gradient descent with momentum. But this has a closed form solution as well. Okay. So here we're going to do the closed form solution, and we actually calculate the MSE, the error, so that we can see what the regularity is doing. So is this clear? Sort of. So this is the estimator, and this is the true model. The true model. That's how things are generated. The theta here is the dummy variable optimization. I'm going to solve it, and I get a theta hat, which is hopefully like an estimate of theta star. So how do I solve this in closed form? It's a quadratic function of theta. Differentiable. It's actually convex, and it's going to be actually strongly convex because of this term. So it's going to have a unique minimum if lambda is bigger than 0. It's really nice. There's just one global minimum. You just have to tell me what it is. How do we do this? closed form solution. And like the notes that I'm going to post, actually simplify my life a little bit. This is going to be argument. I can factor out one lambda. So I get lambda 1 over n lambda here. Plus theta squared. And I'm going to drop this lambda. Why can I drop this? Because argmin doesn't care about like the argmin of this, and that function is the same because it's like a one-to-one map. The minimum would change, but the minimizer doesn't change because it's a one-to-one map. Furthermore, what I would do is I would so minimize, in fact, the function that maps theta to y minus x theta squared plus theta squared to make things more confusing. Why I would do this, if I solve this, and then in the solution, I rescale y and x. So minimize this and change x to x over root and lambda, y to y over root and lambda. If I change these x and y, replace these with these, you can see that 1 over root and lambda comes out, you get that factor there. So it's a trick to simplify. So I'll solve this simpler problem, and then in the solution, I just replace x and y with those, and I get the solution of my original problem. So that I don't have to carry 1 over n. So this I'll let you figure out for yourself, but how do I solve this? So like a simple quadratic problem. This is a function that I want to minimize. You can just solve the original problem. I just want you to see this trick. What is the like your go-to approach to optimization if things are differentiable? Like optimization 101. Gradient descent is optimization like 102. Like before you know about gradient descent, like
So they equal to 0.
differentiate so they equal to 0. Objective, say it equal to 0, the derivative would be like 2. If you believe me, x theta minus y plus 2 theta is equal to 0. That would be x transpose x plus I times theta. I can drop the 2's and move the other side x transpose y. And then I get that theta is equal to x transpose x plus I inverse x transpose y. So do this transformation. We get theta at lambda is equal to x transpose x over n lambda, because I changed both to this over root lambda, plus I inverse. And here I get x transpose y, again, n lambda, because I changed both to that. So you can verify for yourself that this is indeed the solution of the original problem. The trick is like sometimes rescaling helps. If I rescale, I get back the original problem. And furthermore, I'm going to write this as, if I take lambda out, I move one lambda out, I get lambda inverse x transpose x over n plus lambda I inverse, and then x transpose y and lambda. Sorry, lambda is Yeah. So that when it comes out, so I take 1 over lambda out, I get lambda here, and then 1 over lambda comes out and I get lambda. This lambda gets canceled with that lambda. So in the end, the form that I would like to have is this. This is all just algebra. You don't have to worry too much. You can just do it yourself and can verify that this is the solution. Why I write it like this? Because anyone knows why I write it like that? Not like this, for example, or something else. So imagine that, and so X, remember, is like X1 transpose up to Xn transpose. And so imagine that the distribution, so Xi's are 0 mean, assume are 0 mean. If the Xi's are 0 mean, then X transpose X over N, you can argue this would be 1 over N X1 Xn, X1 transpose X1 Xn transpose. This would be 1 over N summation I from 1 to N Xi transpose. So does this look familiar to people? I'm going to call this sigma hat, or sigma hat N. Does it ring a bell? So this is an average. So these are matrices. So this one you can verify. This is like block matrix multiplication. So these are column vectors. What I'm doing rather quickly, I hope at some point you've seen this. These are column vectors, these are row vectors, but you can like multiply them because the dimensions match. You can imagine it's like I multiply a row by like a row vector by a column vector, but really these are matrices. But turns out that I can do it because this is like d by 1, and this is 1 by d. So this gets multiplied by that, I get this, which is d by d. The second one gets multiplied. So imagine just doing like as if it's a vector, like vector of scalars, but it's really a matrix. This is an average. Okay, asymptotically it converges to, by the law of large numbers, to something. What does it converge to? Converges, sorry, to the expectation of one of them, and this is really the covariance matrix of the distribution. It's the covariance matrix, right? So this is really the covariance. If these are 0 mean, this is really an estimator of the covariance matrix of the features. And it's also an unbiased estimator. I'm going to assign a homework problem and show that this is really, without things going to infinity, the expectation is really equal to sigma. I'm going to call this sigma. Have you seen covariance matrices? You should have seen covariance matrices in 1C, right? Covariance matrix is something whose diagonal is the variances, the off diagonals are covariances of the elements. So each one, so here X, you can say generic X. So each one is coming from, so let me do it like a single X. So X1 up to Xn are IID from just the population X. So these are all like, and this comes from the marginal distribution of the feature. And so this really converges to the expectation of this XX transpose and the covariance of the features. So this has some statistical meaning. Similarly, this X transpose Y is 1 over N summation of Xi, Yi. And this is really like a cross covariance. I can maybe write it as like X, Y this converges to the expectation of x, y, which is, so this is a vector, this is scalar, so this is in RD. So this tells you something about the covariance of the response with each of the features. In any case, it doesn't matter what they are, but I can simply write it as sigma hat n, or like sigma hat, let's call this x or xx if you want. Sigma hat xx plus lambda I inverse sigma hat x y. If lambda is 0, this formula is exactly like the usual formula that C wanted to see. If the ends cancel out, but I put the ends so that when lambda is 0, 1 over n comes out and cancels out because x transpose x inverse x transpose y. But with 1 over n, it's better because these are stabilizing around covariances. Okay, so we're out of time. Using this formula, what I want to do next is calculate some sort of an MSE. I wanted to do it today, but we ran out of time. So we have this formula. And what we're going to do is next time I'm going to come back. So f hat of x is really theta hat tilde transpose x. That's my function that predicts everything. The true function is theta star x. So in order to see, what you'd look at is the difference of theta hat and theta star. In this course, we care about the prediction, which is really this function. So I'm going to measure the difference of these two functions. And I want to see what happens. This is really in one-to-one correspondence with the actual risk, which we may get into. But I'm going to measure it in a particular measure, which is easy, which is like the empirical norm, which is just how much they differ on the training data. That's what I want to compute next time. This turns out to have a nice form, especially the expectation of this, assuming that we condition on the training x's. So if you remember the formula that I had, like not just a notation, I'm going to calculate this expectation conditional on the training x's of this. And this turns out to have a closed form solution that we can study and gain insight about what the regularization is. So that's going to be next time. And I'm going to pose some homework problems, and you could start working on some of the details of this. But that's it. Any questions? Comments? We didn't get to see the punchline, but hopefully next lecture we'll see the punchline. Okay, thank you. See you next time.